My name is Jason Flynt. I'm a licensed water well contractor in North Texas, just outside of Fort Worth, and own and operate Barco Well Service. We also founded Resource Monitor several years ago, which is a water monitoring technology company that allows users on our system to remotely monitor water anywhere it's moving through their system. And we also educate at different trade shows and events for continuing ed classes. And last several shows that we've been to, we've had some folks that asked us to kind of dive in on some subjects that we were not able to cover in the meetings and in the education time that we had with them. And so we conceptualized a video series that we're going to call 15 Minutes for Rural Water System Operators. Think 15 minutes with a well guy on several different topics. Those topics are going to be power problems, which today is an issue because of the weather. We're filming in August. It's going to be well over 100 degrees today, and that'll be relevant. I'll kind of connect those dots here in a minute. Source well troubles, another topic that a lot of us may deal with the later we get into the hot part of the year. We're going to cover pumps and motors at some point and really dive into the mechanics of electrical motors and the physics of pumps. Talk about things that maybe rural water system operators would like to know, but they haven't ever had anyone explain it to them. We'll talk about motor controls in one video. Motor controls have come a long ways from the early days of just an on-off switch, and there's a lot of protection and a lot of advantages to some of the technology out there that we have available to us with motor controls. We're going to talk about lost and non-revenue water in a video. Some of those topics come up, very frequently with operators, and we'll talk about some things that we've learned and talk about how we've used our technology to help some folks find and reduce their lost water. And then at the end of the series, we're going to look at technology and our application and how that is a very strong tool for rural water system operators to use in their systems. If you have a topic that's not on this list and you'd like for us to address it, at the end, I've got my contact info. Love to hear from folks in the real world that are actually doing the thing, that are actually working in the rural water system. And if you have topics that a well guy might be able to help you with, send it to us and let us know, and we'll dive in on it and bring that to a video. So rural water systems, let's talk about where we started. And this is kind of a little trivia question. I'll have the answer for you at the end. But where was the first rural water system in the United States? And what year or when was it founded? The answer might surprise you, but in the days of drilling wells, when you actually had to use horsepower literally to drill a well, these guys actually created a water system in a century that it might surprise you. We'll have an answer in a little bit, but since going from 2 horsepower drilling rigs to now remote monitoring and our capabilities with technology now, today we're going to look at incoming power problems, what that might look like for your equipment, and what it looks like on the Resource Monitor app. The way that we bring data into our app, I've got to give you a little background on that first so that everything that we're about to look at makes sense. We have remote communicating smart water meters that either are ultrasonic or magnetic. They communicate with a cell device that's connected to them that sends data up every 6 hours, but it's broken out into 15-minute blocks. That data then comes into our app, and then we put it in an appropriate place for an operator for whatever water asset they have. Currently, we have assets in 15 states and are measuring somewhere between 15 and 30 million gallons a day with our system. So we've come a long ways with technology just in Resource Monitor since its inception. But because we're talking about issues that rural water system operators may see that are relevant today, we got to start with power issues. Today it's going to be well over 100, like I said. And when that happens, there's a few interesting things that you guys may deal with, and you may not know why you're dealing with it, but let's take a look at what those issues might be. We all know what happens at a power plant, right? They generate power. It's then distributed through the grid, kind of probably similar to a lot of your systems that are distributing water. There's different features in the grid that do different things. We see several pictures here of other parts and pieces. We got a solar array over there. We've got some windmills, and then obviously some sort of power plant that's using some firing mechanism to generate steam and turn some turbines. The power that comes out of that utility company or that power plant is alternating current power. Everyone is familiar with AC and DC. DC is what your car battery is. AC is alternating current. And that alternating current coming from the power company, generally in the form of three-phase, is three different legs where that power is alternating directions. That's why we call it alternating current. And so every leg on the grid is changing directions 60 times a second, most frequently. That's what the power company generates. That's the hertz, or the frequency that it's switching directions. And when it comes out of the power company, it is a really clean, smooth transition from, if this is our midline, when it's above the line, it's going one direction. When it drops below the line, it's going the other. And that's a very smooth and predictable and uniform transition. When we look at the grid in terms of how many people are attached to the grid and how the power could possibly be unbalanced, sometimes, especially this time of year when we have high density residential areas, or we have a big user that's only on one part of the grid, those three legs in the grid can get out of balance. And we see it most frequently in voltage imbalance. Voltage imbalance on the power grid, instead of having a really smooth, uniform transition of that power changing directions, we get this amplified wave on one, we get a condensed wave on the other two. And what that amounts to in your motors and equipment that are attached to the grid is that it is not running smoothly. This is a little more closely akin to maybe one cylinder in a piston engine is misfiring, or you have a three-bladed propeller and one of the blades is turned around backwards. It's certainly not going to run like it's supposed to. For water system operators, though, what does a voltage imbalance mean to you? Well, let's take a look at what it looks like when a feature or a piece of equipment in your system is running correctly. And this is our graphical screen console, if you will, on our app that shows down here in the bottom. You can see every 15 minutes we're measuring what's going on at a location. At 2:45 in the afternoon, the flow rate for that 15 minutes was 2,500 gallons. The flow rate was 168, and the total volume at that point in time was 35 million and change. This is what a normal graph shape and detail would look like for a 168 gallon a minute well that's filling up a ground storage tank. We see there's a bar here that's less than max production volume. That was probably a partial 15-minute block. Then it runs pretty steadily. Everything's mostly the same for the runtime that it's filling the tank. Then we see here at 8 o'clock, it shuts back off. Same thing again, you see the block formations because there's a float switch or there's some sort of mechanism inside that storage tank that's telling it when to come on and off. If we look at this graphical representation of it was a well that was feeding a ground storage tank, but they were having troubles figuring out why they weren't getting as much production volume out of the well. They suspected drawdown. But in fact, drawdown was not what was causing it, because you see over here, when we have some full 15-minute blocks, we're kind of maintaining our water production level there somewhere around 185,000 gallons a day. But we get here at 7 o'clock in the morning, 6:45, and we're filling the storage tank up again. Same interval like we saw in the last graph, but now here we're at 11 o'clock. We've got some partial bars here. And what was happening at 11 o'clock, starting about 10:45 or 11 in the morning, the temperature was getting up into the high 90s. And then the HVAC load for all of the residential customers that are on the same grid around this particular well, their air conditioners are running at max capacity here in the hottest part of the afternoon. And what we saw was the voltage getting out of balance. And the well was trying to run because the signal from the storage tank's telling it needs to, but we're seeing these partial bars. The worst part about these partial bars is not that they're losing the production, but more than likely each one of these bars represents several attempts for that pump and motor to start and to move water. Some of them got close to the full 15-minute block, and then we've got some here around 3 or 4 o'clock that are just very, very low volume, and then partial bars for the rest of the afternoon. But then about 6:30 or 7 o'clock, we see full bars come back again. They didn't know why they were losing volume during the day. They just knew that they were losing volume. We were able to put an instrument on there or a meter on this well and then diagnose the problem. This kind of thing that could happen in the middle of the afternoon when there's not someone standing there these are the types of problems that we're able to help water system operators find and fix when we have data that's got this high of granularity. Same issue again, incoming voltage imbalance. And on this well, it was a total imbalance where the well would try to fire in about 3 seconds, because if you take a 150-gallon pump and look at how long of the runtime 8.6 gallons is, about 3 seconds. After about 3 seconds, the well kicks back off because it's outside the boundaries of what the controller would allow the motor to run in. This is a good thing. Someone had programmed the controls correctly. The problem we see, though, is it's firing every so often. And there may be more than one attempt at each one of these, depending on how they had the controller programmed. But we see frequent starts like this during the day. That's a bad situation to put a motor in as well, because what happens to an electric motor at startup, and starts on an electric motor, think miles on a vehicle. Every time it goes from 0 RPMs to 3,600 RPMs in half of a second, there's a huge amount of electricity that's dumped into that motor to get it spinning initially. And when that huge shock of electricity or load of electricity goes into the motor, it deposits heat in the motor. The motor then needs to run for a certain period of time. Submersibles need to run for a certain period of time so that they have cooling water flowing across that motor so the motor doesn't overheat. But if you rapid start a motor too often, you're shooting the large charge of electricity into the motor, then it stops and it's not allowed to cool off. Do it again, do it again, do it again. And then pretty soon you start building up heat in that motor. Heat is the enemy for the insulation on the windings in the motor. And you also get, no production out of a motor that's trying to start not actually moving any water. Same thing again here, but we're seeing a little different signature on this graph. These small bars here are attempts for that motor to run, and they're with some regularity. They keep firing every so often trying to move water because it's being told to move water, but yet until the conditions get right at some point during the day, it actually is unable to fire. Same thing again, kicked out. Then we have several bars in a row where it's at max production or at normal production, and then again, more evidence here that it's trying to fire. Again, too many starts on electric motors they're bad for the motor, it's bad for the windings, and we also have other issues that can manifest themselves with power that's out of balance. Last thing I'll tell you about motors, when you have incoming power that looks like this, where you've got frequencies and the wavelength is off, nothing is matching, is that it's going to create a tremendous amount of vibration. You can get into a situation where these particular waves are opposing each other, and you can have a situation where a motor is being pulled in a direction with 2 of the 3 legs of power, and the other leg is actually trying to pull it backwards. You get vibration, you get heat, you're starting to tear up all of the internal parts of the motor. Power imbalance like this is a bad deal. And we can see it happening in 3 different signatures there with our app. There's normal, there's a series of starts due to high temp and high load on the grid. This is a complete out of balance, potentially maybe some parts on the electric grid failed completely, and it's completely out of balance, won't even run but for a couple of seconds, and then maybe some condition here, again, temporary condition where it's not able to run at full capacity because of the power imbalance. And back to our trivia question. The answer to the trivia question is the first RWS was created or founded in 1763 in Pennsylvania. Now, interestingly, when we have a bad day as an RWS operator, we may have to go get a couple of joints of pipe, or someone has to get on a backhoe or grab a shovel to go fix a leak. Back in this time, these guys were moving water around by gravity through hollowed out logs. And the way they would make connection between the logs was with rawhide. So when we have to go to the supply house, it's not that bad compared to where we started as an industry back in the late 1700s. Rural water systems literally outdate the founding of the United States in 1776. So that's how old our industry is. But the technology that we have available to us now can help operators with everything from diagnosing incoming power issues, mechanical issues with their pumps and motors. We can help rural water systems watch their customer connection. We can help operators see mineralization and drawdown and condition changes in the aquifer. We're going to cover those things in the future here in another couple of videos. But this is my contact information. As I said, if you don't see something on my list here of videos that you'd like to see, send me an email or give me a call, because we are water guys that got into technology, and we would love to share some of the stuff that we've learned in 15, 16 years of being in the water well business with you guys when we can. Again, there's my contact. We are a resource monitor. Let us know how we can help.